Welcome to today's Explainer. We've got a really fun one lined up today. We are going to explore the strictly physical explanation of exactly how we see the world around us. We're going to take a fascinating journey of light together, starting from the incredibly precise biological camera sitting right inside our heads, all the way up to the stunning, expansive canvas of the sky.
Okay, let's dive into this. I know it sounds like a strange question, right? But the truth is, the very same rules of physics that dictate how the soft, jelly-like lens inside your eye focuses on a screen are the exact same rules that paint the sky blue and make the stars twinkle. It is all connected through the magnificent physics of light.
Here's our roadmap for this explainer. We're basically taking an inside-out journey. We'll start with the anatomy of the eye, look at how we fix vision defects, and then explore prisms and rainbows. Finally, we'll scale up to the entire Earth to check out atmospheric refraction illusions and the science of scattering.
Section 1. Anatomy of the eye, or the biological camera in your head.
Now, what's really interesting about the human eye is just how much it acts like a highly sensitive camera. The mechanical perfection of how this works is honestly incredible. Light first enters through a tough, transparent outer bulge called the cornea. Behind that is the iris, a dark, muscular diaphragm acting just like the aperture of a camera, controlling the size of the pupil. Depending on how bright it is, your pupil shrinks or expands to regulate the light. But the real magic happens at the eye lens. This isn't a hard piece of glass. It's a convex lens made of a transparent, flexible jelly composed of proteins. It literally changes shape to focus light directly onto the retina at the back of your eye, sending electrical signals straight to your brain.
But even this flexible biological camera has its limits. Have you ever tried to read a book by holding it right up against your nose? It gets incredibly blurry. That's because 25 centimeters is what we call the least distance of distinct vision for a normal human eye. It's the absolute closest you can look at an object without completely straining your ciliary muscles. Those are the tiny muscles responsible for stretching and squishing that jelly-like lens to focus.
Section 2. Fixing vision defects. What happens when the biological camera glitches?
So, what happens when things don't work perfectly? Sometimes, due to age or just the physical shape of the eyeball itself, our natural lens fails to focus light exactly where it needs to go. This breaks down the two most common glitches. First, we have myopia, or short-sightedness. This happens when the eye lens has excessive curvature, or the eyeball is simply too elongated. To fix it, we use a concave lens. On the flip side, hypermetropia, or farsightedness, occurs when the focal length is too long or the eyeball is too small. We correct this using a convex lens.
Let's move on and see how this builds in practice. Just to establish a baseline, in a perfectly normal eye, parallel light rays coming from a distance enter the lens and get refracted, or bent, so that they converge into a sharp, perfect focal point resting exactly on the retina.
But in a myopic eye, things go a little wrong. Because the eyeball is elongated, those light rays converge way too early. The focal point basically stops dead right in front of the retina. By the time the light actually hits the back of the eye, the rays have crossed and started spreading out again. And that is exactly why distant objects look super blurry to someone with short-sightedness.
To correct this glitch, we place an artificial concave lens in front of the eye, which you know as glasses. This artificial lens intentionally spreads the incoming light rays out, just a tiny bit, before they even hit the eye. By diverging the light early, it forces the eye's natural lens to push that focal point further back, landing perfectly on the retina. It's just a brilliant physics-based solution to a biological problem.
Section 3. Prisms and rainbows. Let's talk about how light breaks apart. Shifting our focus outside the human body now. What happens when light bends through natural glass prisms? Well, it turns out bending light doesn't just focus it, it can actually break it apart. When a beam of white sunlight passes through an angled glass prism, something spectacular happens called dispersion. Because colors of white light travel at slightly different speeds through the glass, they bend at entirely different angles. Red light travels the fastest through the prism, so it deviates the least. Violet light is the slowest, so it bends the most. This separates the white light into a beautiful expanding band of 7 colors: violet, indigo, blue, green, yellow, orange, and red. The classic Vibgyor spectrum.
And this brilliantly illustrates exactly how a rainbow works. Nature doesn't need solid glass prisms. During a sun shower, every single tiny raindrop acts as a floating prism. Sunlight enters the water droplet, refracts and disperses into the spectrum, hits the back of the droplet causing total internal reflection, and then bends one last time as it exits.
Millions of these tiny suspended water droplets work together to paint that massive, beautiful natural spectrum across the sky.
So this brings up a fascinating question. If a tiny droplet of water can bend light enough to make a rainbow, what does the entire Earth's atmosphere do to light? Like, why do stars twinkle in the night sky, but planets maintain a steady, solid glow?
Section 4. Atmospheric Refraction Illusions. The atmosphere as a giant lens. It turns out our atmosphere isn't just empty air. It's a giant, shifting blanket of varying optical densities, acting as a massive, unpredictable lens. Because stars are so incredibly far away, they act as tiny, single-point sources of light. As their light enters Earth's atmosphere, it hits layers of air with wildly different temperatures and densities. This constantly changing atmosphere refracts or bends the starlight slightly this way and that way, moment to moment. This shifting refraction makes the star appear to rapidly change in brightness, which we see as twinkling. It also bends the light downwards toward our eyes, creating an illusion that makes the star's apparent position look slightly higher in the sky than it actually is. Planets, on the other hand, are much closer to Earth. They act as extended sources of light, almost like a collection of many point sources. All those slight variations in refraction average out to zero, completely canceling the twinkle.
And get this, the atmosphere's ability to act as a giant lens also plays tricks with our sun. Because the atmosphere bends light around the curvature of the Earth, we actually see the sun about 2 minutes before it technically rises above the horizon, and we continue to see it for 2 minutes after it has physically set. Atmospheric refraction literally gives us 4 extra minutes of daylight every single day. No way, right?
But light isn't just bending up there. It's also crashing into things, which leads us perfectly to the ultimate childhood question. Why is the sky blue, while outer space is completely black?
Section 5. The Science of Scattering. Painting the Sky.
To answer that, we have to look at the Tyndall effect. This is what happens when light travels through a medium and collides with particles, scattering in random directions. So, the crucial point is that the size of the particle dictates which color gets scattered. The Earth's atmosphere is absolutely full of incredibly fine particles, specifically nitrogen and oxygen molecules, and these molecules are the exact perfect size to catch and scatter the shorter wavelengths of sunlight, which correspond to the color blue. They scatter this blue light in every possible direction, so whichever way you look up, that scattered blue light is entering your eyes. Space is entirely black simply because it's a vacuum. There's no atmosphere and no particles there to scatter the sunlight.
But wait, if the sky scatters blue, why are sunsets red? Well, a sunset is essentially an optical illusion of distance. When the sun is directly overhead at noon, the light travels a pretty short distance through the atmosphere, scattering some blue, but mostly appearing white. But when the sun drops to the horizon at sunset, the light has to travel through a vastly thicker slice of the atmosphere to reach your eyes. The distance is so great that almost all of the blue light is scattered away and completely lost from your line of sight. The only light that is capable of surviving that long, grueling journey unscattered are the longer wavelengths, the reds and oranges.
And we actually use this very same physics principle in our everyday lives on the ground. There is a reason traffic lights and danger signals are painted red. Because red has the longest wavelength in the visible spectrum, it is the absolute least scattered by fine particles like fog, rain, or smoke. It cuts right through the visual noise and travels the furthest distance without distorting, ensuring you see the warning long before you reach the danger.
It is honestly incredible to think about. From the shifting, jelly-like lens right inside your eye capturing the glow of your screen, to floating water droplets painting a massive rainbow, to the nitrogen in the air filtering a sunset into a brilliant red. It is all just the magnificent, predictable physics of light bending and scattering.
So what does this all mean?
It definitely makes you wonder, if our eyes are just biological cameras capturing refracted light, how much of our everyday reality is actually just a beautifully tuned optical illusion? I really hope this explainer has changed the way you look at the sky and even your own vision. Thank you so much for joining me today, and keep exploring.